Hi, good afternoon. I'm Jong-in Lim. Today, I'm going to talk about graph-based representation learning. I received my PhD here 6 months ago under the supervision of Professor Jin-Young Choi. During my PhD period, I did research about representation learning schemes that leverage graph modeling, where a node in the graph represents its data sample and edges represents relationships between them, such as feature similarity or class information. My motivation is that leveraging the relational information between data samples through the graph modeling can improve the quality of the learned feature representations. In this talk, I'd like to share two of my recent works, which were published in AAAI 21 and CBPR 22, respectively. First, I'm going to talk about class-attentive diffusion network for semi-supervised classification. To handle the graph data, graph neural network is a promising tool, and many GNN models have been widely studied recently. Most seminal examples are graph convolutional network and message passing network. The key to both methods is neighborhood aggregation, which updates the node features by averaging the neighboring node features. Recently, many studies have been conducted to extend the neighborhood aggregation. These methods can be categorized into three groups. First, rather than simple averaging, several works have introduced weighted aggregation based on feature attention. On the other hand, some works have extended the range of aggregation to more distant nodes. And finally, recent works have utilized graph diffusion. Instead of feature aggregation, diffusion-based methods update node features by the diffusion process in the graph. Theoretically, k-steps of feature diffusion means that features of up to k-hop neighbors are aggregated to each node. However, there have two limitations. The first is the oversmoothing issue. When stacking multiple layers of GNN, the smoothed areas goes large, and eventually, the node representations in the entire graph become indistinguishable. The second limitation is that existing methods apply the same update rule to every node in the graph. Since each node in the graph is connected to neighboring nodes in different ways, as shown in the figure, applying the same update rule is not an optimal solution. In this work, we propose a new GNN model overcoming those limitations. First, to overcome the oversmoothing issue, we propose class-attentive diffusion, whereby the transition is more likely to nodes probably of the same class. Secondly, to overcome the fixed update, we propose an adaptive update scheme that leverages different reflection ratios for each node, depending on the local class context. First, let's talk about class-attentive diffusion. In the previous diffusion-based methods, the transition probability was defined to be uniformly random. And therefore, the entire diffusion process is determined only by the graph structure. In contrast, our design objective is to make a transition to the next node by comparing the class of the neighboring nodes, making it more likely to move to a node of the same class. The key idea here is that by attentively diffusing to nodes of the same class, it prevents undesired mixing of interclass features, and thus alleviates the oversmoothing problem. To do so, we define the transition probability from node I to j be the cosine distance between pi and pj, where pi denotes the class likelihood distribution given the node features. However, since the true distribution of pi is intractable, we approximate the pi by exploiting the node classifier gpi that is jointly learned during training. Simply put, we designed the diffusion process that determines the next node by comparing the class likelihood given the node features by utilizing the classifier. As the learning progresses, the class prediction of gpi becomes more accurate, and thus the diffusion process gradually becomes class-attentive. In addition to class-attentive diffusion, we further propose an adaptive update scheme. This figure shows a visualization of 10 training nodes with their one-up neighbors. As expected, in real graphs, each node exhibits a different local class context. For example, as shown here, some nodes are mostly connected to the nodes of the same class. For those nodes, aggregating features from neighbors is beneficial to accelerate proper smoothing. However, some nodes are connected to nodes of various classes, or even worse, nodes of the same class may not exist in their neighbors. In these cases, aggregation may lead to corrupted representations due to those interclass connections. Therefore, we propose to adaptively adjust the reflection ratio of the division result for each node depending on the local class context. To this end, we define the update rule for node I as follows. Here, gamma I controls the trade-off between its original feature and the division result. For the node having many neighbors of the same class, gamma I becomes a large value to accelerate proper smoothing. In the opposite situation, gamma I is adjusted to a small value to preserve its original feature and avoid undesired mixing. Finally, based on the class attentive diffusion and our adaptive update scheme, we construct a new GNN model named class attentive diffusion network. In experiments, we validate our GNN model on the semi-supervised node classification task. First, we conduct ovulation studies to demonstrate the effectiveness of each proposed component. First, we compared our class attentive diffusion with 4 existing diffusion methods. As shown in the table, our class attentive diffusion contributes to large performance gains. Also, there have additional performance improvements when applying our adaptive update scheme. Overall, the results clearly demonstrate that the both proposed components contribute to better feature learning. Next, we compared our method with the state-of-the-arts. In this table, we compare the results under the standard benchmark settings. For all data sets, our methods outperforms the state-of-the-art by a large margin. To further demonstrate the effectiveness, we then explored the ability to maintain the performance with a smaller number of label samples. As can be seen here, our methods show robust and superior performance even under the very sparsely labeled setting, which clearly supports that our methods could learn better representations capturing long-range dependencies. Now, let's move on to our next topic, hypergraph-induced semantic tuplet loss for deep metric learning. The objective of deep metric learning is to train a deep embedding network to yield discriminative features, whereby the embedded features from semantically similar images are close to each other, while those from dissimilar ones are far apart. This discerning capability of the embedding network is mainly achieved through loss functions. Recently, many attempts have been made to design optimal loss functions for deep metric learning. Triplet loss is a seminal example, and many extensions have been made to leverage more relationships beyond the triplet. Now, let me introduce our motivation. As can be seen in many prior works, taking advantage of relationships between data samples is critical for metric learning. Especially, our key idea is that leveraging multilateral relations among multiple instances that are semantically relevant may lead to better feature learning. Let me take those 4 images as an example. When considering these 4 images all at once, you will find out that the green class birds have a white head. Simply put, our motivation is that by leveraging multilateral semantic relations, the embedding network can be trained to capture important visual semantics from the input image. To achieve this goal, we propose hypergraph-induced semantic tuplet loss, which we call HIST loss, that leverages multilateral semantic relations via hypergraph modeling. First, to model such relations, we define a semantic tuplet for each class, which consists of multiple samples that have semantic relations to that class. Then, we introduce hypergraph modeling. A hypergraph is a generalization of a graph where each hyperedge can connect more than 2 nodes all at once. In this work, we design that one hyperedge models each semantic tuplet, connecting all the samples included in the semantic tuplet all at once. Now, let's take a closer look at our His laws. Our His laws utilizes multilateral semantic relations between every sample and every class for a given mini batch. These multilateral relations between sample and class can be formulated by a matrix, where each element of the matrix represents a relation value from 0 to 1 that represents the semantic relation between the sample and the class. Then, we define each column of the matrix as a semantic tuplet. We will take the green class as an example. Inside the semantic tuplet, it consists of mini-batch samples with different relation values. Positive samples have definite relation values, and negative samples have soft relation values based on their likelihood belonging to the class. We designed that the more likely to belong to the class, the greater the relation value, since it means more semantic relations. To achieve this, we propose to learn prototypical distributions which approximate the true feature distributions of each class. Specifically, we formulate each distributions to be modeled by a mean and covariance, where the mean represents the class prototype and the covariance represents intra-class variations. Then, the semantic relation value is determined by the distance between the sample and the learned prototypical distributions. After that, we model each semantic tuplet by a hyperedge, connecting all the samples included in the semantic tuplet, where their connection weights are determined by their relation values. In this hypergraph, we formulate a node classification objective employing the hypergraph neural network. Now, I'm going to briefly overview our His laws and summarize the main points. Given a mini batch, the features are embedded through the CNN model. We then construct a semantic tuplet for each class based on their distributions in the embedding space. Then, we form a hypergraph where each hyperedge stands for a semantic tuplet. In this hypergraph, our His loss is defined as a node classification loss employing the hypergraph neural network. The overall pipelines for computing the His loss are fully differentiable, and the whole parameters are jointly trained in an end-to-end manner. Notably, by leveraging multilateral semantic relations, our His loss drives the embedding network to capture important visual semantics and attend to meaningful object regions, which we will show in the experiment section. Now, we share our experimental results. We validate our method on 3 public benchmarks for the metric learning and evaluated the image retrieval and clustering performances. To validate the effectiveness of our His loss, we compared our method with 6 ablation models. Specifically, compared to the single and graph-based classification baselines, our model trained with His loss showed large performance gains. It clearly demonstrates the benefits of the proposed hypergraph approach. To understand the qualitative effect, we investigated the feature activation maps of the test set images. The results clearly show that the embedding network trained with our His loss provides better semantic focus. To further demonstrate the effectiveness, we evaluate the model robustness to various input corruptions. Specifically, we consider these 9 input corruptions that were not used in the training. Our His loss showed robust and superior performances even for the unseen noises, suggesting that the embedding network trained with our His loss attends to the meaningful object regions rather than to distracting noises. Finally, our His loss achieved state-of-the-art performance under the standard evaluation setting for all benchmark data sets for the metric learning. Now, let me briefly summarize the main point and conclude the talk. In this talk, I have introduced 2 graph-based representation learning schemes. Through these works, I confirmed that graph-based representation learning schemes, leveraging the relational information through the graph modeling, are actually beneficial for learning better feature representations. And the proposed methods achieve state-of-the-art performance in semi-supervised classification, image retrieval, and clustering tasks, respectively. Well, that's all for today, and thank you for your attention.